Hello everyone. Welcome to the week 6 of problem solving session of Introduction to Fluid Mechanics. Myself Kalpita Nath. I am research scholar at IIT Kharagpur. So, okay, let's wait for 5 minutes for people to join and then we'll start with today's session. Okay, we'll wait for 5 minutes, okay, for others to join and then we'll start. Okay, I think we should start with today's session. So, have you taken sir's class this week?
Yes, ma'am.
Okay, so we'll go through a brief detail of what sir had taught, and then it will help us in problem solving. There are numerous number of questions today that we'll be solving this in this class. So, okay. So first of all, what sir taught was he started with a few examples of continuity equation. So that you already, if you have taken the class, so you will already have a brief idea of that. But let us go through a bit of detail over there. So first example was where there was a fixed plate at top and a porous plate at bottom. So like that, and a fluid was traveling from like through that porous plate inside, and this is the height between the plates, and it was leaving as it is this, the upper wall is fixed, so it will be leaving through this and this direction. Okay, so this is y and this is x. So what is happening, we are assuming that whatever is entering through this second, whatever is entering through this right side, rather, will be, whatever will be entering here will be leaving from here and won't be leaving from this side, for similarity, like symmetrical point of view. So if you are considering this, keeping that in point, like that point in mind, so we'll be considering now a control volume first. So let us consider this is a control volume, and this, let's suppose I is the fluid that is the side from where the fluid is entering, and E is the side from where fluid is exiting. Okay, and B is the width here. Okay, so the velocity is uniform along y direction, as we can see here. That means the velocity profile is here, like that. It is uniform in y direction, and pressure is also considered as constant, and the flow was considered to be inviscid. So what do we need to do? Like here, velocity is given as uniform velocity v0, and here when it is leaving here, it will be ux. I hope that's visible. Ux, u is a function of x. It won't be a function of y, as we can see the velocity is uniform in y direction. So let us consider the fluid entering through the surface I and leaving through surface E. And because of the symmetry, we are, as I've already told, we are considering the whatever is entering the right side exit through right side only, and not through the left side. So now, okay, so if we'll do the mass balance, so whatever is entering in that surface I, that means density into area into velocity, the mass flow rate, will be equal to whatever is a fluid that is exiting. Okay, so as the fluid is inviscid, so obviously rho will be constant, so rho will be cancelling out. So this will be A1 U1 is equal to AE U E bar. So if we consider the width, width of the plate is given as B. So AI is BX and AE is BH. H means this distance. So that's why area of E, that is this side, is BH. Okay. So if the fluid is entering the porous plate with an uniform velocity V naught, then AIUI is BX V naught. And if it's already given that ux is the uniform velocity that is exiting from the side B, E. Okay, so if that is the case, then AEUE bar will be is equal to HBUX. So now as per this equation, what will happen? Bx V naught is equal to HBUX. So from here we'll get the equation of ux, simple. So it will be V naught x upon h. So this is the x component of velocity. Okay, so let's suppose if the velocity profile was given as this, then we have to track the change of the velocity of the x direction will also be changing with y. But as here the velocity is given as the velocity profile is given as uniform like this, so that's why it is not changing in y direction. Okay, now we need to find the y component of velocity. So if we'll apply the continuity equation, del u del x plus del v del y is equal to 0, and density is constant because the flow is said to be inviscid. So u is equal to v naught x upon h. So del u del x is equal to v naught upon h. Now in this equation, if we will put this, then v naught upon h plus del v del y is equal to 0, and thus del v del y is equal to minus v naught upon h. That means v is equal to minus v naught upon hy plus c, and this c will be a function of x. Now if we will apply boundary condition, what we know that at this wall like, well, let me use some other color, this upper wall, this is basically static, that is fixed wall. So obviously if the wall is fixed, the velocity at this wall it will be 0 as per no slip boundary condition. So we'll be applying that only here. So v at h is equal to 0 as per no slip. Okay, so if we'll apply the same thing here, so this will be 0 minus v naught plus c, or c is equal to v naught. Therefore, if we will apply in the main equation, this is minus v naught upon hy plus v naught. So that's why v of y will be is equal to v naught 1 minus y by h. This is the main equation. Now we need to find the acceleration also. So how we will do that? Simple. Acceleration is equal to, one will be temporal part, that is del u del t. This is along x direction, that's why del u del t, and another will be the convective part. So that will be del u del x, u del u del x plus v del u del y. So obviously there is no velocity variation around y directions, this will be 0, and there is no temporal variation, this will be 0. So only this part will be there. So this is v naught x upon h multiplied by v naught upon h. So this is v naught square x upon h square. Similarly, along y direction it will be del v del t plus this is acceleration along y direction. So there will be acceleration along y direction because of the velocity factor in y direction vy. So this is del u del v del x plus v del v del y. So this is 0 because there will be no velocity component, like no velocity variation of the y component along x direction. So that's why this is 0, and temporal variation is also 0. So this is v dv dy. So that is v naught 1 minus y by h into minus v naught by h. Okay. So this will be is equal to v naught square upon h y upon h minus 1. So how come we'll find the total acceleration? That will be simply ax, that is component along x direction I cap, sorry, I cap, plus along y direction j cap. So anywhere in any condition, like the next problem that sir have solved was the problem of a nozzle. So whatever condition or whatever problem they may give, anywhere we'll just take one small like control volume and we'll do the balance over there. So nothing else. That will give us the velocity component, and velocity will in turn give us the acceleration. So for the second example,
Ma'am,
yes, tell me.
like instead of uniform profile, if it was parabolic, then I didn't get that. What will happen?
If okay, you did
Like you said something,
so.
ma'am. If
Yes,
it was
yes.
parabolic,
If the profile was parabolic, then this velocity, this u directional velocity, will be varying with y also, na? Like here, this one, this u is varying only with x. Right, we have neglected the component along y direction because the u won't be varying along y direction, because here as the velocity distribution is given, it is uniform in y direction. That is a u velocity. There's a velocity component along x direction that is not varying with y. So if the profile will be parabolic, that means like that. So what is happening? At this point, the velocity is different, this point different, this point different. That means along y direction also, the velocity u is varying, right?
but
So
here we found out u of y also.
no, we have neglected, no? We have found out because v is the y component of velocity. You understood the difference, right?
Okay, 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 ma'am.
when
Okay.
when fluid will entering from here, it will be moving in this direction and this direction as well, right? So this direction, what will be moving, like in the upper direction, like let me use some other color. It is visible, right? I'm using
Yes,
yellow,
ma'am.
yeah. So what will be moving in this direction, that we are considering as v, and whatever moving in horizontal direction, that we are considering as u. Understood?
Okay,
So
ma'am. Yes, ma'am. Got it.
u is not varying with y, because as here the velocity profile is given as uniform. If not, it was given as uniform, that means if it was parabolic, then we had to consider, like we couldn't neglect this part. Let me show you. This part we have neglected, no, because u is not varying with y. This we
Okay.
couldn't neglect at that time. Okay. uh yes,
Thank you,
proceed.
ma'am.
No, not a problem. Okay. If anywhere you are facing any doubt, you can ping me like that. Like you can stop me and you can ask the question. Okay. So next example that sir talked about was, so there is a nozzle and here fluid is entering the velocity u infinity, and we can see that the area is changing. Like here, if we consider the area is a naught, and oh, this is the axis, central axis. Here it is x and here it is y. So like if we'll consider one, what we'll do in any of that case, this kind of problem, we'll just consider one control volume. So here we are considering this control volume. If we're considering this control volume, let's suppose on this surface fluid is entering, so this is one, on this surface it is leaving, so that is two. We are taking pressure to be constant around here, and area function is given, it's already given as 1 minus bx. Sorry, not this one. A is equal to a naught 1 minus bx, and u infinity, that means the velocity that is entering is also varying with time, so that is given as c 1 plus at. So what we need to find? We need to find ax, that is the acceleration along x direction. Here also we are assuming in viscid fluid. That is the variation along y we will be neglecting again. So because here we are considering uniform velocity profile again. Okay, so no velocity variation will be along y, only the velocity will be varying along x. So from the continuity equation we can again write the mass balance as rho u infinity a naught. That means that is entering in this area, 1. So we have considered this area as a naught. So this is rho u infinity the velocity that is entering on that side, the uniform velocity, and whatever is leaving from side 2, that will be ux, because we don't know the what is velocity that is exiting there, and we also don't know the area. Okay, so its function is given here, so we'll be using that. So now u infinity a naught is equal to ux, cause density is equal, so density, like, cause flow is inviscid, so density will be cancelled out. So we'll get ux as u infinity a naught upon ax. So this is u infinity a naught, and ax is already given as a naught 1 minus bx. So this is, and u infinity is given, u infinity is given as what? C 1 plus at. That is a function of time. C 1 plus at. This a naught will get cancelled out, so ux will come out to be c 1 plus at upon 1 minus bx. Now we need to find what? We need to find acceleration. Okay, okay, I'll ask you to find this. Can you do that? So velocity we already know, and we already know how to find the acceleration along x direction. Can you find that? Priyanka?
Ma'am, give me, ma'am.
Okay, you do that. I'm here only. Okay. Just we need to take temporal variation and the convective acceleration. And as I already said, the velocity won't be varying in y direction. So we'll be neglecting that again.
Ma'am,
Tell me.
CA by 1 minus dx
Hmm.
plus c square into 1 plus at whole square into b divided by 1 minus dx whole cube.
But one point you missed is one minus will come here because of the minus of b.
Then I got minus b again
Mm-hmm.
because of minus
Only one,
dx.
only once. Of course, you are doing the derivative once, right? Not twice. So as you are doing the derivative once, so because of minus b, one minus b will be multiplied there, right? Check once.
Ma'am, then 1 by 1 minus dx derivative.
No, no, not like that. Let me show you. See, this is del u del t plus u del u del x. So what is del u del x? That del u del x means, u means what? U means c 1 plus at upon 1 minus bx. So if we will find this, this will be c 1 plus at So we have to derivate with respect to x. That's why t will be remaining constant here. So, one second. So what will happen is this one will derivate. So this will 1 minus bx whole square, right?
It will be minus
But
1 by 1 minus bx whole square.
yes, minus b will be multiplied with it. So because of this minus b, there one minus will be coming at front.
No, ma'am. Derivative of 1 by x is minus 1 by x square. No,
So minus 1 by x square, but this b will also come.
ma'am.
Okay, you are saying as minus 2, right? Okay, okay, I understood. Then it is my mistake. Understood, understood. So there'll be one plus. Yeah, correct. So this will be ac upon 1 minus bx, and this will be plus, correct. I've written something wrong here. Okay, so this is bc square, as you correctly said. So this is 1 minus bx whole cube. Is it the one?
Yes, ma'am.
Okay, okay. Okay, then this kind of questions will solve like that. And next, we'll move forward to the topic of angular deformation of fluid elements. So, if we consider this to be a fluid element, and this is delta x, this is a b c d, this is the fluid element, and because of deformation, what is happening, the new fluid element is coming as this one. This will be like that. So what is happening, from horizontal it has moved to an angle delta alpha, right? And from the vertical it will be forming an angle delta beta. That means it was initially 90 degrees, so this means pi by this is 90 degree minus delta alpha delta minus delta beta. Okay, and this is given as delta y, and this one, this distance is given as b delta t, b delta t. Okay, so this new element is a dash, b dash, c dash, and d dash. And this, if we'll consider a triangle, this is a dash. So this one, this distance from this distance, this is v plus del v del x del x del t. Now we need to find out what our main aim here is, find out how much deformation took place when it is deformed. That means del alpha and del beta. So it will be changing with time, right? So we need to, after that, we need to find the rate of change of alpha. That means del alpha del t and del beta del. So if we'll consider, let's suppose this triangle, that means triangle AEB. If we'll consider triangle AEB, B dash, AEB dash. So B dash E dash means which one? B dash E dash means this one, this portion. So this portion will be is equal to v plus del v del x del t minus v delta t. It's already given, right? That this whole distance minus this distance. So this will give us this distance. So this will come out to be del v del x del t. Similarly, a dash will be del x plus some higher order terms. This del x some plus some distance. So that we are considering as some higher order terms. So if we'll find 10 del alpha, that will be b dash e dash upon a dash e dash. So that is equal to del v del x del t plus del x plus higher order terms. So this higher order terms we are neglecting, and as del alpha is very small, so we are considering 10 del alpha as del alpha. So we are considering this del alpha upon del t, this will get cancelled out, is equal to del v del x. So this is alpha dot, that is the angular deformation of alpha with respect to time. Now similarly we'll find for beta as well. So beta will be is equal to del u del y. This is the two very important thing that will give us the angular deformation and will be numerously used in the problems further that we'll solve. Now another thing that we are going to use is the rate of angular strain or angular deformation. The rate is alpha plus beta, the addition of alpha plus beta. How? So first of all, what is the change? The change means initially what it was, what the angle was, minus finally what the angle is. So initially what it was? Initially it was 90°. So pi by 2 it was initially, minus finally what it become? It became pi by 2 minus del alpha minus del beta. So this will be pi by 2 minus del alpha minus del beta. So this will come out to be del alpha del beta. So this is just change. So if you will find the rate, so this will be del t upon del t. So this will be alpha dot plus beta dot. Simple. So this we already know as del v del x, and this we already know as del u del y. So we are denoting it as epsilon xy. Similarly, we can also find epsilon yz and epsilon xz. In short, epsilon ij is equal to del uj upon del xi plus del ui upon del xj. And epsilon ij is equal to epsilon j. Now, if we'll consider that the fluid element that we are considering is behaving as a rigid body, then there will be no deformation, right? Just there will be rotation. Like as previously what happened, it got deformed like that deformed. But now it won't be deformed. It will just rotate like from this to this kind of. So if that is taking place, like for the rotation, what we will do? For that rotation, we'll consider alpha dot is equal to minus beta, cause as this angle is not changing, so like if this is the body initially and when it rotated, it became like this, it suppose became like this. That means this is del alpha and this is del beta, right? What it was initially, finally also it is same, that like the angle whatever will be taking place here, the same thing will be taking place here, but it will be opposite. Like if this direction we are taking as positive, beta we should take as negative. That's it. That's why alpha, the rate of change in deformation in alpha will be equal and opposite to beta. That is for rigid body. Like if the fluid element is considered as a rigid body, then only this will be applied. So there is no deformation, just rotation. So if we are being asked to find the rotation, like what if whether a body is rotational or irrotational, what we will do? We'll simply find this. That means half of alpha minus beta. Why minus beta? That means if this is the like this is the new deformed body, this is del alpha and this is del beta. If we are considering this positive and del beta is negative, so that's why we are considering alpha dot minus beta dot. So this will be half of alpha is given as del v del x minus del u del y. So this is considered as wxy. Similarly, wij for if z is also considered, then del uj del xi formula will be like this: del ui del xj. Okay. So if the body is rigid, then what wxy will be? At that time, if the body is rigid, then obviously alpha dot is equal to minus beta dot, then this will be half alpha dot minus beta dot, so that will be half alpha dot plus alpha dot, so that will be alpha dot. So if we do parametrization of the deformation, then it is del ui upon del xj. So that is equal to half of del ui del xj plus del uj upon del xi. You're understanding that, right? Are you facing doubt in any place?
No, no.
Okay. So half of del ui, we are just doing the parametric analysis. So del uj, this is minus del uj del xi. So this is similar to what? This is similar to rotation. And this is similar to what? This is similar to deformation. That means this is epsilon ij and this is wij. Okay, so next, another very important thing that will come into picture over here is vorticity. So vorticity is what? Vorticity is del cross p vector. That means what? That means the curl of velocity vector, the cross product of velocity vector with divergence. So this, what we will do, we will use this, we can use this to check even whether a flow is rotational or not. So if we'll break down curl, it will be ijk del x del y and del z. So this is uv w. So simply we'll just break it down like I cap will be this into this minus this into this into this minus this into this. So this will be, if we will break this down, so del w del y minus del v del z plus j del u del z minus del w del x plus k del v del x minus del u del y. So this will be what? This will be nothing but 2wyz y, cause w we know as half of this one. So if we will write this up, that will be twice of wxy, right? So simply we are writing this. So this is twice of wyz, and this is I cap plus 2wzx j cap plus 2wxy k cap. So this is 2w vector. So if we want to get a real feel of what vorticity is, vorticity is basically what? Vorticity is the local rotation of a fluid element. That means it will tell us whether a fluid is spinning or not. Like if we do, even for vorticity, if we will do divergence of vorticity, del cross v, sorry, this will be, this is 0. That means the vorticity is free of divergence. Also, another thing that we want to form here is circulation. So what is circulation? This will be numerously used in problems. That means if there is a element, line element that is taken here, and this is the velocity vector, so the line integral of this velocity vector and the surface element, like the line element, is called circulation. This can also be written as the surface integral and curl of velocity vector multiplied by the n cap is the normal vector on this surface multiplied by ds. This is also the circulation. So this is nothing but we have applied what? The Stokes theorem. Now let me give you some examples of what vorticity is, to get a real feel of what happens over there. Like if there is a fin in a stream of fluid, like if this is a fin in a stream of fluid, like if I draw fluid like this, then there will be wakes that is developing here. They'll be rotating. They'll be rotating about their own axis. Apart from the rotation, apart from like rotation like this, they'll be rotating about themselves also. Like this is called vorticity. To get a more real feel, like if this is a surface and this is the velocity profile in that surface, there is a fluid that is coming from this side, and let's suppose there is a little floating thing that moves with the flow. Like we have placed a tracker over here. Like let me use some other color. If this is red, I'll use black over here. Okay, so I have placed one tracker here, and I want to see like how the tracker is moving about its axis. So if this point is we are considering as 1 and this point we are considering as 2, what is happening? As we can see, the velocity is not uniform about y direction. So velocity at 1 and 2 are different. Why? The velocity at 1 is different than 2. That means when 2 like we are like if there is a person standing here, if that person is close to point 2, he will have a more gradual feel of no slip boundary condition because of this wall. So the velocity at point 2 will be less as compared to velocity 1 at point 1. So what will happen? This will rotate. This one will rotate, right? This tracker will rotate. So now if I'll move to the next location, how I can see that tracker? Like this is the black part and this is the red part. If I'll move further, it will be like this. This is the red part. Okay, sorry. This is the red part and this is the black part. So you can see, right, how that is changing. So if I'll move more, then this will be the black part and this is the red part, because every time there will be a difference in velocity between the 2 points, between the top point and the bottom point. So it will keep on rotating. That means what is happening? There is a continuous rotation of the fluid element. This is what vorticity means. That is, the fluid elements are moving about its own axis. This is vorticity. If let's suppose we are considering one ocean, like the top layer of ocean, then like let's suppose this is a ocean, this is air and this is ocean. Let's suppose we the fluid element that is present here will be rotating like this. Like if I consider a fluid element here, it is like that. If I'll be considering here, it will be like this. That means what is happening? Can you understand what is happening here?
It is zero vorticity.
Yeah, correct. Because it is, though it is rotating about the like in a circular motion rather, but it is not rotating about its own axis. So vorticity is not present there. That means vorticity function here is zero. But at the same case, if we are let's suppose there is one boundary and there is another boundary here and some fluid is coming from this side and it is coming like this. So what will happening? There is some interesting phenomena that is happening over this side. So like there will be circular motion in the fluid element here. Like means the fluid will move like this, like this. So if I draw the fluid element over here, we can see like let's suppose if it is like this, here it is like this, here it is like this, here it is like this. Can you now see what is the difference between these two cases?
There is rotationality, which there is vorticity in the second case.
Yes, like fluid is, the fluid particle is rotating among like in a circular motion, along with that it is rotating about its axis. That means there is vorticity present. Vorticity here is not equal to zero. So you can get a real feel of like you can understand now, right, what the vorticity physically means.
Yes, ma'am.
Okay, so even if we uh, if we take streamlines here, like let's suppose there is a streamline and this is the velocity, like the tangent to the streamline will give us velocity. So this is the velocity vector, then the velocity vector and vorticity will be perpendicular to each other, right? That means this is the vorticity, they are perpendicular to each other. So with that we'll then move forward. We'll then move forward to next topic, that is stream function. Do you have any doubt in vorticity or the previous things that I explained?
No, ma'am.
Okay. I'll devote like what all things that are left. Let me check. Mm, okay. We'll go for 15 more minutes, then we'll proceed with the problem solving. So let us get a quick recap of what further will unfold. So let's take a 2D incompressible flow. That means the 2D continuity equation is del u del x plus del v del y is equal to 0. That means u here is like if we are defining like that, that is psi is the stream function, psi x function of x and y both. So this is u and v is minus del psi del x. This will satisfy the continuity equation automatically. So d psi, if we will write, that will be is equal to del psi del, like if we will differentiate it, dx plus del psi del y dy. That means this is u, this is v minus v. Sorry, this is v, this is minus u. So this is equal to v dx minus u dy. And if we will write along a streamline, like there is along a streamline, if these are the streamline 1, this is streamline 2, there is a no variation of stream function. So if we are considering along a streamline, then d psi variation in psi will be 0. That means v dx minus u dy is equal to 0. That means dx upon u is equal to dy upon v. This is the equation of streamline. So in order for psi to satisfy the continuity equation, psi should be second order differentiable. What does that mean? That means del psi del x del psi del y minus del del y del psi del x. If psi is second order differentiable, then only this will come to 0. Right? Left hand side will be is equal to right hand side. That means the flow field will be, or the velocity field will be satisfying the continuity equation. So it should be second order differentiable. So if we have the have a line element, so how the volumetric flow rate is related to stream function? Let's have a look at that. Like if this is a line element and we are considering 2 points 1 and 2 over here, and this is theta, this is dx, this is dy, this is n cap, and this is dl, and this is theta, this theta, then this theta. Okay, so this is if 1 and 2 points are sufficiently close, then b is the width, bdl n cap, bdl is the area. Okay, bdl n cap will be the area if a and b, this point a and b, or 1 and 2, whatever we may consider, are very close to each other. Then n cap can also be written as, what can we write it? Let me check. So if this we consider triangular element, this is theta, this is theta, this is n cap, and this is dl, this is dy, this is dx. So n cap is equal to minus sine, see, sine, here if we will write sine theta is equal to what? Sine theta is equal to dy upon dl, this is dl, and cos theta is equal to dx upon dl. So if we will write n cap, that will be minus sine theta I cap plus cos theta j cap. So the volumetric flow rate, if we will write, the volumetric flow rate is equal to simply area into velocity. So what is area? Area is b dl n cap means minus sine theta I cap plus cos theta j cap. So that multiplied by u I cap plus v j cap. So this will be is equal to bdl minus u sine theta plus v cos theta is equal to b minus u dl sine theta plus v dl cos theta. Simply like we have multiplied dl inside. So this dl sine theta is dy and this dl cos theta is dx. So we'll just replace this. So b minus u dy plus v dx. That means dq, if we will write dq, this will be d psi. Okay. So if, cause this is d psi. So if we will integrate this 1 to 2, 1 to 2, the element, so that is q2 minus q1 upon b is equal to psi 2 minus psi 1. Now, let's suppose I give you an example. Let's suppose u is equal to a question. Okay. So the velocity is given as u. U is given as like x component of velocity is given as d. And just 1 second. Okay. Y component of velocity is given as y cube minus 4z. Right. This component. Okay. So and z component is given as 3y squared z. So we first like the question is the flow one dimensional, two dimensional or three dimensional?
It has three velocity component now. So it should be three dimensional.
Okay, just 1 second. This will be 0, sorry. So it will be two dimensional.
Two dimensional.
So second question is the flow incompressible or compressible? What do you think? For that, what do we need to do? We need to find the
Yes.
continuity equation. Yes. So what do you think? It is compressible or incompressible?
Incompressible one.
Yes. So we'll do the divergence of v, that will be is equal to del v del y plus del w del x. So this is minus 3y square plus 3y square, that is 0 simply. Now next thing is, if possible, if this flow field is possible, find psi, that means the stream function. So tell me what will be the stream function? Can you find that?
Just a minute, ma'am.
Sure, sure.
Minus y cube z minus 2z square.
Minus y cube z.
Minus
Correct,
2z
correct,
square.
correct, correct, correct. So what we will do here, this is first of all, what we will do is v is del psi del z and w is minus del psi del y. So if this is the case, then this will be v dz is equal to d psi. So if we will integrate this, so v is given as minus y cube minus 4z. So this is minus y cube minus 4z dz is equal to d psi. So from here, if you'll integrate this, psi will come out to be minus y cube z minus 2, sorry, minus 2z square plus function of some function of y. This is equation 1. For w, this is minus w dy is equal to d psi. So this is equal to minus 3y square z dy is equal to d psi. So this psi will be is equal to minus y cube z plus function of z. So this is equation number 2. So if z is equal to 0, psi is equal to 0. So if we will put that in both of the equation, we'll find that fy is equal to 0 and fz is equal to 0. So psi will come out to be minus y cube z minus 2z square. The last thing that will be there is, one second.
Ma'am,
Yes, tell me.
a stream function, like in the class, sir told that it is like here that we are defining it for 2D incompressible
Yes,
flow.
2D incompressible flow. It is valid for
So,
that only. Like here
okay,
it is 2D, no? Like u we are not considering, u is 0. That's fine.
uh, no, ma'am. Like my question is that whether it is valid for 2D incompressible only, or is it difficult to calculate for 3D? That is why we are considering
3D it
2D.
can't be. It can't be. It is defined only for 2D.
Okay,
Hmm.
okay.
So next thing is forced vortex and free vortex. I think I should not go in. Have you taken the classes of that?
Yes, ma'am. He has. Sir has taken one example.
Okay, sure. Then I think I won't go to the much detail because it's already 8:15 almost. So let me give you an example. If B is AY plus B I cap plus AX J cap, can you find the rotation? Whether this flow is rotation or not. Okay, so I'll come back in 1 minute. You solve, okay?
Yes, ma'am.
So you have to find rotation and then stream function, and another thing is that circulation sorry, about the curve bounded by y is equal to 0, x is equal to 1, y is equal to 1, x is equal to 0. So these three things we need to find out. Okay. So I'll give you 1 minute, you solve this and I'll come back. Okay. Okay, so have you solved it?
Yes, ma'am.
Okay. So what you
It
got
is.
for rotation?
It is irrotational.
Yes. So for rotation, simply we'll find out wxy. So that is half of del v del x minus del v del y. That means half of a minus a. The iPad is lagging. Okay. So this will be 0. Even vorticity also, if we'll find out, that is also 2w, that is also 0. So as vorticity is 0, the flow is irrotational. Simple. So Second question was about the stream function. So have you found out the stream function? First you'll check whether the flow is possible or not. If it is possible, then find out the stream function.
It is two-dimensional incompressible flow.
Yes, it is two-dimensional incompressible flow.
So we can find stream function.
Hmm.
Stream function is ay square by 2 minus ax square by 2 plus
Hmm.
by.
Plus some constant. So constant we need to mention.
Okay, that's constant.
Okay, and third part?
Third part circulation 0 because vorticity is 0.
Yeah, correct. Okay. So then let's move to the next topic, that is velocity potential. So this is the last thing for today. So velocity potential. So velocity potential for irrotational flow, like if you're considering irrotational flow, then curl of v vector is 0. And if curl of v vector is 0, del v del x minus del u del y is equal to 0. Del u del x minus del w del y is equal to 0. And the rest. So I won't go to much detail about that. If we will do parametric analysis, so u will be is equal to, like, we are defining velocity potential. So if we'll define velocity potential, u is given as del phi del x, and v will be given as del phi del y, and w will be given as del phi del z. So as we can see that the velocity potential is like can be established for three-dimensional flow as well. So the flow is not required to be two-dimensional as it is in case of stream function. So this definition should satisfy the irrotational flow. That means the flow should be irrotational, then only this thing is valid. So if del cross v is equal to 0, then v is equal to divergence of phi. So v is a conservative fit. So if we'll consider a two-dimensional incompressible flow, then psi, that is the stream function, is valid. And if we'll consider an irrotational flow, then phi is valid. And if we consider both, then both psi and phi are valid. So other things, like, okay, so d phi can be represented as, like, if we'll do the differentiation, del phi del x dx plus del phi del y dy. So this is equal to u dx plus v dy. So if phi is equal to constant, d phi is equal to 0. Then u dx plus v dy is equal to 0. That means dy dx at phi is equal to constant is equal to minus v u by v. So, and if psi is constant, then we already know v dx minus u dy is equal to d psi. So dy dx at psi is equal to constant will be v by u. That means if you will multiply both uh, du dx at phi is equal to constant multiplied by du dx at psi is equal to constant, that will be is equal to minus 1. So that means what? That means they are orthogonal to each other. Like if this is the equipotential line, that means the velocity potential is constant, And if this is the stream function, that means psi is equal to constant, this will be 90 degree. So if u is given as del phi del x and v is given as del phi del y, then we can write this as del x square. Like if we write the continuity equation, okay, if we'll write the continuity equation, this will be del u del x plus del v del y is equal to 0. So this will be del x whole square plus del y del square del x square del square del y square. This pi is equal to 0. That means del square phi is equal to 0. So this have to satisfy the Laplace equation. And if the flow is irrotational, that means del u del y minus del v del x is equal to 0. The writing pad is being too slow. Okay, bear with me. So this is del x del x square plus del y square psi is equal to 0. So that means del square psi is equal to 0. So both of the stream function and the potential function, velocity potential function, both of them should satisfy the Laplace equation. Okay, much of the detail. So let us proceed to the question. There are lots of questions today. So I'll be sharing this. This is the first question for today. So what does it say? An infinitesimally small fluid element as shown in the figure is subjected to the velocity field u is equal to kx plus y, v is equal to minus kx plus y, and w is equal to 0. So this is a two-dimensional field. So these are the questions, 6 questions that are associated with this. So can you tell me what are the answers of each of the question? Can you solve this?
Uh, First, linear strain along x direction,
Hmm.
option A.
Yeah.
Along y direction, minus k,
Hmm.
option B.
Hmm. Solve the rest.
Ma'am,
Yes.
uh, for question number C, it is
Hmm.
option B.
Option B. I don't think so. Check once.
Sorry, ma'am. Option C. For
Yes.
question number D, it is option B.
Yeah, yeah, correct. And question number E, E and F.
E, it is option B, and F, it is option A.
E is option B. No.
Angular velocity.
Angular velocity is half of alpha minus beta. So alpha is minus k and beta is also k. So minus k it will be minus 2k. So half of minus 2k means minus k.
Minus 2.
Yeah. So next is the vorticity of the fluid element. What about that? What you got?
It will be minus 2 km then.
Yeah, correct. Okay, so this is done. Let us proceed to the next question. So determine the stream function.
Ma'am,
Yes, tell me.
here I got stream function as k into x square by 2 plus y square by 2 plus xy.
K into. K will be cancelling out now. Check once. When you will do dx upon u is equal to dy upon v, that is the main equation for stream function. So there k will be cancelling out now. Check. Have you done?
Ma'am, stream function or streamline?
Stream function. See, it's written in the question. For stream
I did.
function, we'll write in the, like, we'll use the stream function, like, we can use the streamline equation as well. So for my solution, I have used that.
Okay, I did that u is equal to d shy by dy that way.
Don't go in much like complications. So see here, you don't need to find the psi. So you can go for that also, but the easier approach is if you'll use the streamline equation. So have you got the solution? The k will be cancelling out over there.
Yes, ma'am. In that case, k is getting cancelled out.
So what is the final equation that we are getting? I think, wait 1 second. It will be stream function. I think it's written wrong. Yes. It will be streamline only. You are correct. Because stream function will be psi will be including over there. Okay. Let us consider streamline only. So what is the equation of streamline? What have you got? Final equation.
as a streamline, no, ma'am. X
Yeah,
square,
yeah. Hmm. X square.
x square plus y square.
Hmm. Then
I got plus 4xy, ma'am.
it will be plus 2xy. Check. It will be x dx plus y dx plus x dy plus y dy, right? So y dx plus x dy will be combining together to form d of xy. So then it is x dx plus d of xy plus y dy, right? So if we'll be integrating it, then x dx will be x square upon 2, and y dy will be y square upon 2, and the middle portion it will be just xy. So 2 will just multiply. Have you got it?
Okay, ma'am. Yes, ma'am.
Okay. Okay, let's proceed to the next question then. Mm. Which among the following figures correctly represent the shape of the fluid element subjected to the given flow field? So equation is the same as earlier. Here it said that k is less than 0. So how we will understand like which of the following will be the uh, before like final fluid element?
By calculating the linear and angular
Yes,
strain.
yes. So we have calculated that already earlier. So can you tell me which is the correct answer? Yes.
Among option A or B, according to linear strain,
Hmm. But there will be angle also na, that we need to consider. That means alpha dot, beta dot. What do you get in that? What will be alpha dot? Tell me.
alpha dot will be option A, ma'am, answer. We'll get alpha dot as minus k.
And
So
beta dot.
here it is less than beta dot is of k.
So alpha dot minus k. That means angle change will be positive, right? Because k is negative.
Yes, yes,
So alpha will be positive. But at the same time, beta will be negative, no?
yes, ma'am.
So beta change is negative. So beta will be in opposite direction. So won't we get option D? Because I am in doubt. Because whatever they sent us the solution, that is option. They have given us option A. But according to me, it should be option D. Because beta is negative. So beta will be the opposite of alpha, right? What do you think? Have you understood?
Yes, ma'am. I understood, ma'am. Like one, it will be positive, but if it is negative, then it should have come in the clockwise direction.
So if you are taking alpha as positive, that means in the clockwise direction, then beta should be in the anti-clockwise direction, no?
Yes, ma'am. But in the as per linear strain, only A is coming correct, ma'am.
Linear strain one is negative. That means there is contraction, and yeah, that is also true. So in AB there will be contraction, and in there will be elongation in B, like AD rather.
Yes, ma'am.
Okay. But actually, they have alpha and beta. Beta they have not even given here. Both of them are alpha only. So yeah, option A should be the correct one. Because check, this is D alpha. Both of them are D alpha. Beta have not even calculated. They have not even calculated. Like have not shown here, I guess. Can you see? Hello?
Oh, sorry, ma'am. Beta is negative, ma'am. Yes, ma'am.
Beta is negative, like,
Yes,
but
ma'am.
they have not considered beta here.
Yes, ma'am.
I think that's why they got A. According to
Yes, ma'am.
me, if they consider beta, then it should be option D, but rather A B dash will be a bit less.
Yes,
Then
ma'am.
option B, D will be correct. Like, because there is contraction in AB side.
Yes, ma'am.
But according to me, option B is correct. Sorry, D is correct. Let's see. So, if this kind of question comes, then you understood, right? How should we solve?
Yes, ma'am.
Okay, then. So, I think here most probably they have considered alpha on both sides. That's why they have taken it. Most probably that may be the case. Because as we can see, if we'll zoom this out, we can see here both of them are alpha, D alpha. So I think in that way they have considered maybe. Okay. So this is the question number 4. So which among the following statement are correct regarding stream function and velocity potential function?
Uh, A and D, ma'am.
Yeah.
Sorry,
So no, no,
B
no.
and D.
Yeah, correct, correct. And the second one, which among the following is the correct regarding the free forced vortex? Which one is free and which one is forced? Where circulation is
Uh,
present?
A and C, ma'am. Circulation is present in force vortex.
Yeah, correct, correct. Okay. Um, Observe the streamlines and velocity profiles for two incompressible steady two-dimensional flows, both of which have circular streamlines in r theta plane. So vorticity, the equation of vorticity for cylindrical component is given. So what do we need to find? Now choose the most appropriate option from below. Flow A describes a solid body rotation and B describes a line vortex. Or A is rotational, B is rotational, A is irrotational and B is rotational everywhere except at the origin. Option C1 is option A correct, but B false. So what do you think? And option D is flow A is an example of free vortex, but flow B is an example of forced vortex. So what do you think? Which one is correct? So you have to calculate here, right? So you have to calculate here the vorticity, right? To check whether the flow is irrotational or rotational, you have to check the vorticity.
By looking at the picture, we can get to know, no, ma'am. Like as you explained,
Mm. Tell me which one then?
flow A is rotational. Flow B is irrotational.
Flow A is
Rotational.
A is rotational and B is,
Irrotational.
so which one, which option you think is true? A is rotational,
Option
that
C.
is true. Option C, correct, correct. So you have got nice understanding of this then. So but if they want us to quantify, then we can simply calculate, like the equation is already given, so using the vorticity equation we can simply calculate the vorticity and check which one is irrotational or rotational.
Ma'am, what is line vortex?
Which one?
Like, there's a word like line vortex. What is meant by that? Line vortex.
I'll tell you, just one second. Hmm. Okay, so if the velocity, like if we are considering as let me show you. Is the writing pad visible? think I.
Not visible, ma'am.
Just I'm connecting it. Okay, so the line vortex is basically like how should I explain it? It is a vortex that have constant circulation rather. Like circulation we know already. So if the circulation strength, that means this that we already calculated from that formula is there one, na? Just
Yes,
one
ma'am.
second. So if that is constant, the strength is constant, acting along an entire length. Like if this is the flow field and there is constant circulation over there, like that.
But for like option like the flow B, since it is rotational, like we get circulation as zero, no?
Which one?
Since flow B is rotational,
Hmm.
we get circulation as zero, no?
Circulation at zero won't be possible. As we can see, like even you can see from the velocity diagram, you can see that when we are coming at origin, the velocity is infinite. Can you see that from the diagram?
Yes, ma'am.
So if the velocity is infinite, it is undefined. So at the center, we cannot calculate the rotational characteristics. So it will be undefined at the center,
Okay.
except at the origin. So yeah, B is correct. So you understood
Okay.
what is line vortex, right?
Okay. It's like constant
Constant,
circulation, no?
constant circulation, nothing else.
Okay, ma'am.
Yeah. So yeah, let's proceed to the next question. Mhm. So two-dimensional velocity field is given and the rate of angular deformation and vorticity we need to find out. So you can solve this for me. So this is in the similar context it is. So can you tell me what the answer will be? What is the rate of angular deformation? Rate of angular deformation means del v del x plus del u del y, right? We've already learned about it.
-6.
Hmm. And what is the vorticity then? It means del v del x minus del u del y, correct? So what will be the
Minus
answer?
3x.
Correct. So that is option B. Okay. So velocity field in a fluid medium is given as this, the whole vector, and the flow is incompressible rotational or incompressible irrotational or what? So for compressibility, what we'll do, we'll use the uh, del u del x plus del v del y, right? Continuity equation. So if you'll use the continuity equation and we'll see that it is coming 0, then obviously the flow is
Incompressible.
incompressible. Yeah. So it is incompressible. And what about the rotationality?
It is rotational.
Okay. Yeah, correct. So should I solve it or it is fine?
Fine, ma'am.
Okay then. Let's proceed to the next question then. Okay. A two-dimensional velocity field is given as we can see here. The expression for stream function for such a, the question is visible, right? Oh, yeah. The
Yes, ma'am.
expression for stream function, the expression for stream function, we need to find out. Tell me, what is the solution? So this is nothing but u we already know, v we know. So del u del x and del v del y we'll find out. We'll first check whether continuity equation is valid or not. Then the flow is valid, otherwise it's not. So if the flow is valid, then we'll go for the stream function definition, what we already know.
A, ma'am, option.
Option A, correct. So you have a great idea of this now. So let's proceed. Uh, okay, I think it's visible. I don't know. Okay, so a steady incompressible two-dimensional velocity field is given by as it is given in the question. So where x and y coordinates are in meters and magnitude of the velocity is in meter per second. The linear strain rate in x direction is in second inverse. So what is the linear strain rate then? Very easy.
Minus 1.6.
And what is the vorticity?
0.
Yeah, correct. So linear strain, what we did for that simply del u del x, and for vorticity we'll do del like del v del x minus del u del y. So we got that 0. Okay, so converging duct flow can be modeled by a steady two-dimensional velocity field in the form as given. The pressure field is given by this equation where P naught is the pressure at x equal to 0 and the expression for the rate of change of pressure following a fluid particle will be which of the following? So what we will be using here, tell me? This we have done in the previous week. Can you tell me? Have you understood the question? Hello, Priyanka.
Yes, ma'am.
Have you understood the question?
Oh, yes, ma'am. Thinking, ma'am.
So what do we need to do there? Can you tell me?
Um, is it by using dou p by dou t plus u into dou p by dou x? That way we can get the change.
Yeah. The convective part and temporal part. We can use that for anything. So here we just need to find the variation of the pressure. So we can definitely use the substantial derivative. So tell me the answer then. Have you solved it?
Doing, ma'am.
Okay.
Option B, ma'am.
Option, let me check. So I've got rho b cube y square minus x square, rho b cube y square minus x square. Option D. I got option D. Which one you got? Tell me.
Sorry, ma'am, I did a mistake in the
Okay.
sign.
Okay. Not a problem. You check where you did. So answer will be option D. Okay. So you understood,
Okay, ma'am.
right? Okay. So
Yes,
let us
ma'am.
proceed to the next question. So this is a velocity field that is given. So where lengths are in units of meter, time in second, and velocity in meter per second. So there is a stagnation point at minus 0.625 and 1.875, as we can see in the diagram itself. So streamlines of the flow are plotted in the figure. Calculate the various kinematic properties, namely the rate of translational, rate of rotation, linear strain rate, shear strain rate, and volumetric strain rate, and verify that the flow is incompressible. So we just need to do what we have already done in the past questions. So you can do it, right?
Uh, Ma'am, linear strain rate and the rate of translation. Linear
Yeah.
strain rate is dou u by dou x, and
Yeah, the
you dou.
previous week we did it, right? Linear strain rate.
Uh, what about rate of translation? Is it same as linear strain rate?
Shear strain, rate of
Rate of
translation. Okay, rate of translation means, just 1 second. I have not calculated it a lot. Just 1 second. I have not calculated the rate of shear. Leave this one. Next, the other things you calculate, because I have not calculated it, so now I can't say.
Okay.
I have calculated the linear strain rate and the rate of rotation, then the volumetric strain rate and the shear strain rate. Just let me check for the rate of translation.
Ma'am,
Tell me.
uh, flow is incompressible,
Hmm.
and getting linear strain rates as along x point 0.8,
Correct.
along y minus point 0.8,
Correct.
and shear strain rate I got 0.
Yeah, correct. And volumetric?
0.
Okay. Okay, fine. Okay. I have to check for this translation when I get back to you. I'll check this once. So consider the following steady state incompressible two-dimensional velocity field is already given. So check whether the flow is irrotational or rotational. Second part is not required. Streamlines you don't need to sketch. Just the first part, whether the flow is rotational or irrotational. Tell me that.
It is rotational.
It is rotational. Yeah, it is rotational. So what you got, WXY? What is the value you got?
I got vorticity as minus 2y.
Okay, correct. So this next question. Solve this. So same thing. vorticity we need to calculate, and we need to check whether the flow is rotational or irrotational. Obviously, if we'll check vorticity, we will get to know whether the flow is rotational or irrotational.
Here, you said we are taking it as 0.
Tell me what?
Like
Yeah,
what we are
vorticity is
taking.
coming at vorticity is coming as 0. Yes.
No, no, I'm
So
asking along z direction, what is the velocity?
along z direction is not required, no? Only r is given and theta is given. So we'll use the equation I have introduced to you in the previous question. Do you remember the equation? Wait. This one, this equation. So we'll use just this equation, nothing else. So z is not required itself.
Okay. Could you please share the question once?
Yes, yes, 1 second. Have you written the formula?
Yes, ma'am.
Yeah.
Getting 0, ma'am.
So it said, like as I've given it a read, in the previous question, we needed to calculate the translational vector, right? So it is how much the fluid has moved. So it can be denoted by the velocity vector as it has denoted in the book. So it said that if the fluid element, like if the velocity vector is ui cap plus vj cap plus wk cap, that much distance. That means it will move from the origin, right? So from the origin we'll consider. So u, v, and w will be the values that it has moved in x, y, and z direction. Understood?
Okay, ma'am. So that is the rate of translation.
Yeah, rate of translation.
Then rotation, ma'am.
Cause u obviously is dx rotational to the formula that we have used till now.
Ah, same that
Same
omega,
thing. Yes,
whichever.
yes,
Okay,
yes, yes.
okay.
Translation, I was a bit doubt, but cause sir have not taught that in the class. But this is the basic thing. Cause u is dx upon dx upon dt, right?
Yes, ma'am.
So that is the rate of change of x. So that will give us the value, how much it has translated. Okay.
Okay.
Okay. Now, have you calculated this? What is it?
0, ma'am.
Okay, so this is the next question. So the velocity field in a fluid medium is given. So we need to find the translation velocity, the rotational velocity, and the vorticity. Translation I have already told you how to calculate. So we'll just find the velocity vector. You give the value. So 1 to 1 is given. So in x, y, z, you'll just put the values. And t is also there. So you'll just put the values. So you will get some u, some v, and some w, right? So those are the translational velocity vector values. Understood? And rotational velocity vector, we already know w.
Yes, ma'am. For translation, it is 12i plus 4g plus 13k.
Correct. For the rotational velocity, So for rotational, what we will do? Half of del cross V, the curl of V, right? So the curl of V means ijk, half of ijk, del x, del y, del z, UVW, right? So we'll just determinant of that, we'll just break the determinant. So UVW we already know the formula. So you can find it out, right?
Yes, ma'am.
Okay. So tell me the answer.
Um, what is it here got as 2i minus 8k?
Tell me again, how much?
2i minus 8k.
No, it will be I minus 4k. Not a problem. You check it once,
That is
know.
rotational, no, ma'am.
Oh, so vorticity only, right? Acha, acha, you are telling me vorticity.
Yes, ma'am.
So vorticity is, yeah, 2i minus 8k. And what about the rotational?
I minus 4k.
Okay, so, okay, we have more questions left. So let's proceed to this. So similarly, we have to find out the vorticity again. So we'll use the same formula. So W we already know, like half of del, like curl of V vector, we'll just multiply it by 2. That is twice of that. That will give us vorticity. You remember that, right? That means simply curl of
Yes,
V
ma'am.
vector will give us vorticity.
Yes, ma'am.
So find that out.
Minus 21 I minus 2j minus 5k.
Wait, it is 21.
Minus 21 I
Huh?
minus 2j
Hmm. Minus
minus
5k.
5k.
Yeah, correct. So, okay. Next question. Tell me. Solve this.
Incompressible one.
Okay. Okay. Correct. Next question. Tell me about all of them. Like there are 5 equations, like values for x, u and v. Tell me which of them are possible, which of them are not.
One is possible, ma'am.
Yeah. Next.
Only one is possible, ma'am.
Rest have you calculated?
I did not get a 0.
Okay. Okay, correct. So yeah, let's proceed to this. Tell me. So this is some different question. So we need to find the flow rate, and we already know the relation between flow rate and the stream function, right?
Yes, ma'am.
So calculate this.
Along AB, I got 16 units.
Along?
Along OB, I got 16 units.
Correct, correct.
OA 0.
Hmm.
And along AB, I got as a 16 units.
Along AB. Just 1 second, let me check. AB is 16 units. Correct. Correct. I also got these values. Okay. So the last question for today is this one. So this is for the velocity potential, because we have not solved any question on that. So we will solve one question on this. So you remember the velocity potential, right?
Yes, ma'am.
Okay, solve this then. First, we need to verify whether the flow is incompressible and then determine the stream function for the flow.
It is incompressible. Stream function is uh, 2xy plus constant.
Stream function is 2xy.
Plus constant.
Okay, let me see. 2xy plus constant, correct. Okay, then it is done for today. So, do you have any doubt in today's session? Anywhere where you are not clear about anything?
No, ma'am.
Okay, then I'll meet you next week, same time. I hope you enjoyed the session.
Yes, ma'am.
Okay,
Thank you, ma'am.
welcome. Bye bye. Good night.
Good night, ma'am.